How's your day? I hope you guys having a good day. And in this video, we would like to explain to you about the metabolites primary and its purification. And before that, I would like to introduce ourselves. Hello, I am Syahira Sinta. You can call me Rara. And with student number B1B02001.
And my name is Mathea Larasati. You can call me Thea with student ID B1B022 and 23. So, today in this video, we will be assisted by two our friends, Riri and Titi. Riri and Titi will help explaining about primary metabolites and purification in fungal purification in the fungus Aspergillus oryzae. So, stay tuned! Before we go deeper, I want to explain a little about primary metabolites. Primary metabolites are compounds produced by living things and have an important role in the metabolic processes and survival for organisms. These compounds function directly in supporting growth, development, and reproduction, as well as maintaining the body's physiological function. Examples of primary metabolites include carbohydrates, protein, lipid, and nucleic acid. Primary metabolites have their own roles and function. For example, protein function as enzymes and constituents of various biological structures. Primary metabolites are produced in large quantities and continuously during the growth phase of an organism, so they are often referred as two central metabolites. Due to their importance, they are the main compounds that make up the living body and support a variety of essential biological activities. In addition to primary metabolites, there is such a thing as secondary metabolites. They are also interconnected with each other and equally important in the metabolism of organization. But this time, we will focus on primary metabolites. The main difference between primary metabolites and the secondary metabolites lies in their function, production, quantity, and ecological role. Primary metabolites are compounds that are directly involved in the growth, development, and reproduction processes of organisms. These compounds are essential for maintaining basic physiological function and are produced in large quantities during the growth phase or trophophase. One of the most striking differences is the timing of metabolite formation. Primary metabolites are formed during the primary growth phase of microorganisms. Secondary metabolites are formed towards the end of the microorganism's growth phase or stationary phase of growth. Examples of primary metabolites in fungi include carbohydrates, protein, fat, and polysaccharides such as beta-glucans. Beta-glucans is a very important primary metabolite because it is the main component of the fungal cell wall and plays a role in the structure and physiological function of the fungus. In addition, fungi also produce the enzyme alpha-amylase as a primary metabolite that functions to hydrolyze starch into simple sugar, such as maltose and glucose, which are then used as energy sources for fungal growth and metabolism. Alpha-amylase is produced during the activity growth phase and it is very important in carbohydrate metabolism in fungi. Alpha-amylase in fungi is a primary metabolite enzyme that plays an important role in carbohydrate metabolism, especially in the breakdown of starch into a simple sugar such as maltose and glucose, which can be used as an energy source by fungi. Alpha-amylase production in fungi is strongly influenced by environmental conditions such as pH, temperature, and incubation time, which also affect growth efficiency and the synthesis of other primary metabolites such as beta-glucan, the main polysaccharide of fungal cell wall. Thus, alpha-amylase acts like a key enzyme in fungal primary metabolism that enables the utilization of carbohydrate nutrients to support biological activity and survival.
Now, we enter the metabolite production by fungi. There are several steps that are carried out for the production of alpha-amylase industrially, namely, selection of suitable alpha-amylase producing microorganism, inoculum preparation, fermentation process, ESSP or SMV, purification, characterization, product packaging and storage, and the last one is application. The next one is selection of suitable alpha-amylase producing microorganisms. There are 3 steps. The first one is isolation, the second one screening, and the last one is identification. For isolation, we could use several methods like serial dilution agar plate, workup solid plates, immersion tube methods, and etc. For screenings, the isolates are screened for amylase activity by flooding the starch agar plates with iodine solution 0.5% and 1%. This shows a clear zone around amylase-producing microorganisms. And for identification, we could use several methods as well, such as biochemical tests with tryptophan breakdown test, microscopic examination, and genetic analysis. In this case, we're using Aspergillus oryzae. As we all know, Aspergillus oryzae is the most important and popular and has been used as yellow koji in producing many traditional fermented beverages and foods, such as Japanese sake, miso, and soy sauce. The two major fermentation industries, Nova Enzymes and Danish Collagen all employ Aspergillus oryzae as their primary production organism. Aspergillus oryzae has TACA amylase A or TAA, which is a major enzyme produced by the mold, is famous worldwide to be leading enzyme for industrial utilization and academic study. Now, we enter the next stage of industrial production of alpha amylase, which is inoculum preparation. There are 4 steps. The first one is working stock culture. The second one is primary culture inoculum. The third one is secondary culture inoculum, and the fourth one, seed fermenter. Now is the third stage of industrial alpha amylase production, where a decision is made between using solid-state fermentation, SSF, or submerged fermentation, SMF. For SMF, it includes soluble starch or sugar, molasses, fruit and vegetable juices, and other synthetic media. For SSF, we're using wheat and rice bran, wheat and rice straw, cassava, barley, oil cakes, sawdust, and etc. For this production, we highly recommend to using wheat bran because it is having high initial starch content of wheat bran, very good buffering capacity, good water holding capacity, and better aeration. Low cost of wheat bran and its composition assortment provide a good source of substrate for various enzymes and organic acids production and other biotechnological application. Next is optimization of fermentation condition by OFAT and statistical optimization methods. There are several things that influence of physiological chemicals parameters on alpha amylase production, include temperature, pH of the medium, incubation period, inoculum age, and the others. The next stage is purification. In this stage, there are 5 important steps you need to follow. The first one is extraction, the second one filtration, the third one precipitation, the fourth one chromatography, and the last one is electrophoresis. First, the enzyme is extracted from the fermentation medium through centrifugation at 10,000 rpm for 15 minutes or by filtration. It is then precipitated using 60 until 80% saturated ammonium sulfate with constant stirring at 4 Celsius to reach 40% saturation, followed by incubation at the same temperature for 18 hours. The resulting precipitated proteins are collected via centrifugation and dissolved in 0.1 m phosphate buffer. Further purification is carried out using ion exchange chromatography or DAAC to separate proteins based on charge, and gel filtration chromatography or Cefadex J100 for separation by molecular weight. Finally, SDS page is used to confirm the enzyme purity and estimate its molecular weight, which is typically range from 50 to 60. This is a little video footage about the SDS page. The fifth one is product packaging and storage. Alpha amylase derived from fungi is commonly prepared in powder or freeze-dried form for industrial and laboratory application. It is primarily packaged in double-layer aluminum foil bags containing desiccant to prevent moisture absorption and vacuum sealed to minimize oxidation. For bulk transportation, secondary packaging typically involves sturdy cardboard boxes or plastic drums. To maintain stability, the enzyme should be stored at room temperature around 25 Celsius if sealed, or at 4 Celsius for extended shelf life. A dry environment with humidity below 60% relative humidity is essential, ensuring a shelf life of approximately 1 to 2 years when kept moisture-free. At last, the purified alpha amylase enzyme serves as a valuable primary metabolite ready to be utilized in a wide range of industry, from food, pharmaceuticals, detergent, textile, and even biofuel production. So this is the effects of the alpha amylase in starch.
So that's all from our explanation. We want to say thank you to our friends Riri and Titi that helping us to explain about primary metabolism and purification. I hope our video are helping you guys, and we were sorry if we made a lot of mistakes during the take of the video. So that's all from us. Don't forget to like, share, and if you have any question, comment below.